Hi Nafa, have you submitted the assignment?
Yes, ma'am.
Okay. Uh, So you got everything correct or is there any doubt?
No, ma'am. I definitely have doubts in this one.
Okay, okay.
Okay.
Okay, so the first question is transformation matrix for clockwise rotation of unit vector along xyz direction by an angle theta with respect to the y-axis. So this question has been discussed in the lectures. Have you watched the lectures?
Yes, ma'am.
Okay. So how do we do it is, so we have to do a rotation with respect to y-axis. So first of all, how do you represent a rotation matrix? Do you know that? How do we represent in matrix notation?
I'm not sure.
Okay, so let us start with there. Okay, so for every, as I told you in the first class, like for every symmetry element, we have to associate it with some numbers so that it's not always that we will imagine a molecule in space, do the rotation, then write the answer for everything, right? So we need to have a mathematical tool to do all these calculations, so that no, if we are not doing it, maybe the computers can do it. So for them, to make it like machine understandable, we need to transform this language of symmetry in numbers. So how do we do that? Is through matrices. So for every symmetry element, we have a matrix that when we operate it on the, like on you can call it the atoms or the bonds, or the whole molecule itself, then that molecule gets changed. Suppose you have a matrix A, and you multiply it with another matrix B, then the resultant matrix will be something different to A, right? It will not be same as before, unless and until A B is not equal to identity matrix, means B is not equal to 1. Identity matrix is represented as like this. So 1 1 1 and so on, and off diagonal elements are all zeros, like that. So it's same as saying that unless and until you multiply a number by 1, if you multiply it with any other number, that number will get changed to something new, right? Similarly, if you have a matrix, suppose 2 3 4 5, and you multiply it with 1 2, right? The what will be the resultant? The resultant will be some matrix which is not same as this, right? The operation of this, the multiplication of this matrix on our original matrix will change that matrix, right? So we consider this as your molecule. So we have to represent the molecule also in terms, or the bonds in terms of some matrix. Suppose this is your molecular bond, as say, let's say molecular bond or atom. Okay, and this is your matrix representing a symmetry element. Okay, so when you do that, when you multiply these two, your molecular bonds or the atoms, they will change their places in the matrix, right? They will change their places, or they will uh, change, the values can also get changed. Okay, so what we are doing here is we are applying this symmetry element on this atom, on these atoms or the bonds, without doing the calculation, imagine like without imagining things, or without graphical things. We are doing things mathematically now. Okay, suppose you have, so as I was telling, so for what do we need here? We need matrix representing symmetry elements. Okay, so for every symmetry element, there should be a matrix, some definite matrix. Suppose you want, as I told, identity is represented as this. So if you want to apply identity on an molecule, you have to multiply it with this matrix. Okay, if you want to do some rotation, suppose C2 rotation on a matrix, on a molecule or on an atom, you should have a matrix which represents C2. So for every symmetry element, we need to have a definite matrix. Okay, so let us start. Suppose for C rotations, for Cn means rotational matrix. Okay, and here I have written N because N can be any number given by 360 by theta. Okay, so here we are dealing with any rotational axis. Suppose it's the generalized form, it can be C1, C2, C3, Cn, anything, right? So these are called transformation matrices. Okay, so what I told, these matrix which represent the symmetry element are called transformation matrices. Okay, so if you want to transform a point x, y, z, okay, now first one, let us start with the easiest, identity. So what I told, you have three sets, three coordinates which you want to transform. Okay, so for that you have to, you need a matrix of order 3, means we will take a 3 cross 3 matrix. So you need 1 1 1, other element should be 0. Then you need to transform what, xyz. So this will represent the original coordinate xyz. Okay, this is your original coordinate. Whose coordinate is this? This can be coordinate of uh, an atom, or it can represent orbitals, anything which the, and this thing, this original coordinate is called basis. Basis means what? It's, as the name suggests, based on what you are transforming the molecule. You are doing, suppose you can rotate an atom around any axis, you can rotate a bond, you can rotate the whole molecule. So based on what you are doing the symmetry transformation on is your basis. So basis can be orbitals, atoms, bonds, and or the whole molecule itself. Okay, now when you multiply these two, you will get some what will be the dimension of the matrix, new matrix? This is 3 cross 3 and this is 3 cross, sorry, 1 cross 3. So this one will be, so this and this are common, so it will be 3 cross 1. Okay, it will be a column matrix, it will have 3 rows and single column. So whatever will be the answer, suppose the answer is x dash, y dash, z dash. Dash means x prime, y prime, z prime, or these are your new coordinates, new coordinates or transformed coordinates of your basis. Basis is xyz. After, on applying this transformation matrix on your basis, you have transformed the basis to a new coordinate, means you have moved the coordinates. You have changed the coordinates. So for identity, since it is the identity matrix, when you will do multiplication, this will get multiplied with this will get multiplied with this will get multiplied with this, okay, and the rest are 0, so there will be no change. So it's simple matrix multiplication. So when you do that, your answer will be same as original, same as original basis, which again says that identity, as told you na earlier, identity element does not do anything. So no change means the coordinates in the basis. So the coordinates are not getting changed here. Identity will not produce any change to the basis or to the original coordinate. Okay, now come to the next one, which is suppose reflection. Okay, uh, when you reflect something, suppose you have F and G, some random imaginary molecule, okay, and this is on this coordinate system x, y, z, and I put a plane which is this plane, means y, z. This is sigma, y, and z. So after doing this, what will happen? O will not change its place because O lies in the plane, right? And F and G will get interchanged, right? So whatever atoms or the bonds lie in the plane does not get interchanged. So what? So let me do some random molecule which is A, B, C, D. Suppose it's a same molecule and you have a plane here. What will happen? C will come here, A will come here, and B and D will not change places because they are on the plane. So what happened here? B and D were on the YZ plane. So YZ did not change. No change. But whatever elements were on the x-axis, they got the x became minus x. So A was here. Suppose this, if this is your origin, and A was originally 5 units in the positive direction and C was at suppose 6 units in this negative direction. So what happened was C came to here -6 for C, and for A it was -5. It became -5. So this is what a plane does. Okay, whatever plane you are applying, that coordinate will not change, the remaining coordinate will change. So how do we represent this? Suppose I apply xy plane. So in this, x and y remains same and z becomes -z. Okay, so in matrix, how do I represent this? 1 0 0 0 1 0. So you remember these diagonal elements are getting multiplied. Sorry. So we want the answer to be x, y minus z, because x should not change, y should not change, but z should become minus z. So we have to put -1 here, and the rest will be 1 and 1. So only diagonal elements are getting multiplied here, because there is no mixing of these two. X is getting transformed to x only, y is getting transformed to y only, z is getting transformed to z only, but with a negative sign. Here it's not happening that y is becoming z or x is becoming y. This thing is not happening. So this is called mixing of coordinates. If mixing will happen, then these off diagonal elements will also become non-zero elements, so that when you multiply anything with that non-zero element, it will reflect in your answer here. Are you understanding, Nafa?
Yes, ma'am.
Okay. So so this is your sigma, this is the transformation matrix for sigma xy. Similarly, you can write a transformation for yz. How will it look? So in yz, what will change? Your x should change. Y and z will remain 1, 1. X will become -1. And rest will be zeros. Fine. So this is how we do the rotation. Next remaining is this one. So here y will change, x and z will not change. So this is how you do rotation. Now this is what 180-degree rotation. Sorry, this was what sorry, reflection, right? Now we will come to rotation. This was reflection. Now identity is done, sigma is done. Now let's come to rotation. Rotation by any angle theta. Fine. So you have to rotate. Suppose you have a, okay, C double bond O double bond something X, here something is there Y. Okay, this is an imaginary molecule. Now here this is the coordinate system XYZ. So if I do a rotation like this on this axis, okay, suppose this is CX rotation by 180-degree, what will happen? How will this molecule look? It will become like this, right? Or rather I should write it like this if you want to keep the end like this. So here the atoms which were on the x-axis, like these atoms X, O and C, they did not change their places, but the atom which was on the y-axis changed their place. Now let me write one more Z here. So Z will come over here. So atoms on x-axis did not change their places. Why? Because we had applied Cx. So what is changing is these two coordinates. So now we have to fix one and change the other two. If it is simple 180-degree rotation, we can write 180-degree rotation means C2 and along x-axis. So C2x. So we have to change y and change these two. So you just put -1 here, keep this 1 here. Okay. Now same thing if you want to do, this is along this axis. So if you want to do along z axis, C2z, how will you write? This will change, this will change, this will remain fixed. So these are the transformation matrix. Now if you want to generalize this, this is 180-degree rotation. So that is because 360 by 2 is 180-degree. But if you want to write it for any theta, then the formula for that is CNZ, cos theta minus sin theta, 0, sin theta, cos theta, 0, 1, 0, 0. So this is what you call as transformation matrix for rotation by an angle theta along z-axis. These two things are important. Okay, what is important here is theta and z-axis, because the rotation is along z-axis, so z is fixed, z is not changing. So here the element is 1 and x and y have to change. That's why x and y is, it has some values. Now here it is not simply 1 1, because as I told, if you rotate by 180-degree, there was no mixing. So here when we rotated by 180-degree, mixing did not occur. Y remained y and z remained z. X was the anyway constant. But if you rotate by some other angle, suppose 120-degree, suppose 60-degree, then if you do that, it will not exactly go opposite to here. It will 60-degree means y will come somewhere over here. So now this coordinate has some value of x and some value of y. So mixing of the two x's will happen. So because to take care of that, to take care of the mixing, we have some values on all these four places. Okay. Now if this was your rotation matrix, your rotation matrix is this. This is your transformation matrix, CNZ. What if you want to transform any point x1, y1, c1 to a new coordinate x2, y2, z2, what will you do? You do the matrix multiplication. So what will happen? Z1 and Z2 will be, this will be same. Second, x2 will become x1 cos theta minus y1 sin theta, and y2 will become x1 sine theta plus y1 cos theta. Now you see the new coordinate x is now a mixture of older x and older y coordinates. So this is what you call mixing of coordinates. Fine. Now how do we arrive at this formula? So that is being discussed here in the question. So the question is asking that deduce a transformation matrix for clockwise rotation of vectors x, y and z by an angle theta with respect to y-axis. So now here I told you about z-axis. Now the question is asking about y-axis. So what happened in when z-axis was our rotation axis? This place was fixed, constant. So if we are doing for the y-axis, what will happen here? It will have some element, here it will be 1 and here it will have some element. Okay. So this is fixed, this is fixed. These two places will have some elements, these four places. So let us deduce that. So first you draw a Cartesian coordinate. Suppose you have a vector. The question is asking about a vector xyz. I had solved it. Let me check. Okay. So since we need to find out Cyn by any angle theta, so means y should be fixed. So let us take this, since y is fixed, let us take these axes as x and z. Okay, x, z and y. Y will not change, these two will rotate. Okay, now you have to rotation along this axis. Now this is my earlier coordinate x1 z1. If you rotate it along the new coordinate by an angle theta, what will it may come over here with x2 minus z2. Right? So this angle is theta because we have to apply a rotation of 360 by n, which is being represented as theta. Now what is these? So if I draw projection of this over here, what will it be? These, so the length, take the length of the vector as L. Okay, so x1, which is this point, how will you write x1? X1 will be L cos theta. No, not theta. Let us take this angle as, take this smaller angle as alpha. So this angle will be theta minus alpha. Okay, so x1 will be L cos alpha, and z1, which is this, z1 will be L sin alpha. This part is L sin alpha, this part is L cos alpha. Next is, you want to deduce for x2. So x2 is what? L cos, same as this one, L cos theta minus alpha. Now you must be knowing about this formula. Cos theta minus alpha is given by cos theta cos alpha plus sin theta sin alpha, and also what else is required? Sine. So sin theta minus alpha is sin theta cos alpha minus cos theta sin alpha. So this is the formula. So let us apply. Here we have cos theta minus alpha, so just replace this over here. So x2 will be L cos theta minus alpha. It will be L cos theta cos alpha plus L sin theta sin alpha. Now here we had L cos alpha was x1. These two you have to replace. L cos alpha is x1 and L sin alpha is z1. So L cos alpha and L sin alpha. So this becomes, x2 becomes x1 cos theta plus z1 sin theta, right? Okay. So now we have to, same way we have to deduce for minus z2. Minus z2. How will you write it? Minus z2 is equals to L sin theta minus alpha. This part, right? This will be L sin theta minus alpha, which is your z. Now same, use that formula, L sin theta cos alpha minus sin alpha cos theta. Okay. Now if I put this minus sign over here, it will be minus, it will be plus. Again, L cos alpha is x1, L sin alpha is z. So z2 is equals to, let us write the positive one, z1 cos theta minus x1 sin theta. Okay. And earlier we know that y will not change, so y1 will remain y2. Now we have these three equations. So you can represent this in matrix notation. So what we are changing what is our basis is x1, y1, z1, and it is getting changed to x2, y2, z2. Now since y1 and y2 is same, these two are same, so this element will be 1. Okay. Now if you multiply x1, you have to multiply x1 with cos theta to get x2, and then you have to add sine theta to z to get x2. So here you write cos theta because it is getting multiplied to 1. So this you imagine as 1, 2 and 3, and here it will be sine theta. So if you do the multiplication, it will be x1 cos theta plus 0 into y1 plus sine theta into x1 will give you x2. Understood? So we are just representing the multiplication already which we have into matrix notation. Now with z1 I have to multiply cos theta. So z1 cos theta. So here this place is a place for z. So this will be cos theta, and with x it will be sine theta. So this place will be, and it is minus sine theta. So this is your notation. Okay. So this is the answer. This is the transformation matrix. Likewise, you can also write a transformation matrix along uh, y-axis. Sorry, along x-axis. Z and y we did, and along x-axis you can also write, and you can also write for anti-clockwise direction. If the rotation is along a anti-clockwise direction, the signs will simply change. Okay. Okay. Now here the question is, consider this carbonate ion. The 3 oxygen atoms are designated 1, 2 and 3. The C atom is designated as 4. So this 1 means an oxygen, 2 means an oxygen, and this 3 means an oxygen atom. And the fourth one is a carbon atom. So this is COO and whole minus is the carbonate ion. Taking the pz orbital of the 3 oxygen atom as the basis. So you have to take the pz orbital. Now here you should recall that what I told is we can do transformation matrix. We can multiply the transformation matrix to any bond or any orbital or the atom itself. So in this question we are doing transformation of the orbital. Which orbital? Pz orbitals of which atom? Of all the oxygen atoms. Okay. So this is your, if this is z axis, this is x axis, this is y axis. Okay, there xyz is ulta, तो कोई बात नहीं. this will work. So bottom one is shaded, suppose. So one is positive low, one is negative low. This is the PZ orbital, and this one is 1, this is 2, this is 3. Taking the PZ orbital as basis, and we have to write those PZ orbital as PZ1, 2 and 3. The transformation matrix this represents. Now here you see that in this transformation matrix, it is not a diagonal matrix, right? You see it has some off diagonal elements, this one and this one. Off diagonal elements mean, off diagonal elements are means that you have what, mixing of orbitals, mixing of coordinate. In this case, the coordinate is an orbital or the basis is an orbital, so we will write as mixing of these orbitals. So mixing of coordinates, isn't it? What is the diagonal element here? This one. This is the diagonal, principal diagonal we call this, and this is a diagonal element which is third row, third element. The third row, third column means it is PZ3, which means that in the answer PZ3 will not change its position, the other two will change its position. So you should recall that in which symmetry transformation only one of the coordinate changes place. Was it a reflection or rotation? In like one of the coordinate does not change
Rotation.
place. Yes. So this coordinate is not changing place, the other two will change place. So it should be a rotation. So the last two options will not work here. It's either
Okay.
first or second option. You can just rule out these two. So either this or this. Now let's check which one is this. If you want to do it a long way, you can check all the four options. Let us start with the first one. First one is C3Z. So C3. Suppose here we have, this is your X, this is your Y according to question. This is PZ1, this is 3, this is 2. Okay, now when you do a C3 rotation along, what is given, along Z axis, okay, clockwise, what will happen here? How will it get rotated? This is the Z axis.
We will get minus x and minus y.
Yes, it will get turned. So here, this is C. Uh, the coordinates will not change its place. So this is X, this is Y, this is C. Now clockwise means this will come over here, this will go over here, like that. Okay, so here we will have pz1, here we will have 3, and here will be pz2. Okay, now what is happening is, you see, in place of earlier which was 1, it is 2, which was 2, it is 1, sorry, which is 3, it is 1, and which was 2, it is 3. So it has got changed in a cyclic manner. See, pz1 has become 2, 1 has become 2, this one. Okay. 2 has become 3, and 3 has become 1. Cyclic order. So how do we write this? Now here my basis is this orbital pz1, pz2, pz3. Okay, after this transformation I know what the answer should be. Answer is this: pz1 should get changed to pz2, pz2, pz2 should get changed to pz3, pz3, and pz3 should get changed to pz1, pz1. Okay, but here there is no mixing, there is no mixing, so two orbitals will not add up to give this. Okay, 1 has become 2, 2 has become 3. It's not like that in place of 1 we have a linear combination of 2 and 3 and 1. It's not like that. So a single orbital has got transformed. So 1, you have to multiply 1. So here this is 1, 2 and 3. Here this is 1, 2 and 3. Row number and column number. For understand this, for 1 to change into 2, we need to give something over here at the place of 2, and the rest should be 0. This element should be 1 and the rest should be 0. Understood? Because how will it remember matrix multiplication? This will get multiplied to this will get multiplied to this, and this will get multiplied to this.
Yes.
Yes, to change 1 to 2, we have to put something at the place of 2. Similarly, 2 gets changed to what? 2 gets changed to 3. So we have to put
3.
something at the place of 3, because this will get multiplied, rest will be 0. So how will it get multiplied here? Like this will get multiplied here, this will get multiplied here, and after adding up we will pz1 into 0 is 0, plus pz2 into 0 is 0, plus pz3 into 1 will be pz3. So the answer at this place will be pz3. Okay, now same way we have to get pz1, so this should be 1, because these two will get multiplied and the rest will be 0. This will get multiplied, yellow lines, this and this. Fine. So the first option itself is correct, C3Z. You can check for option B also. So how will you check that? This is X, this is Y.
Ma'am,
Yeah,
But in the solution, it's given answer is D.
Answer is
D.
no, it cannot be D, no?
Yeah, ma'am, but like it's given in the solutions, it's given like that.
It can
So,
be wrong, maybe the solutions.
okay, ma'am. Okay, ma'am.
You understood? No, we are getting this by okay,
Yes, ma'am.
let's try D. D is given, right?
Yeah.
Okay, let's check D first, whether it's coming or not. Okay, so this is it one? D says we have to apply sigma V, Y and Z. So where will the plane be? Y, Z plane, this plane. Okay, I drew the plane wrong. Y, Z plane. So this is along the z-axis, so let us just draw it like this. See, this is z, this is x, this is y. So if this is the yz plane like this, and the bonds are along cz and between x and y and here. Okay, one bond is along an axis and two bonds are in between the axis. So if you do the rotation, this is pz3, this is pz1, this is pz2. So if you do the reflection, these two have to interchange places. pz1 will come in place of pz2 and pz2 will go in place of pz1. So the matrix and pz3 will remain as it is. So here it should be 1. 1 will become 2, so this should be 1. 2 will become 1. This also is the answer, no? Hmm.
Ma'am, actually, for the option, the first option, it's not the same matrix, ma'am. It's different, actually. What we call it. It's like,
Which one? C3?
yeah, ma'am. It's not the same, right?
Oh, okay. Okay. I wrote a different matrix, but okay. What is, yeah, it's a different matrix. Sorry. Yes.
Okay, ma'am.
Okay. Then this is correct. The matrix. Okay. For C3, 1 is here, right? Okay. But you understood, no? That's how we get it.
Yes, ma'am. Okay.
Can you find for this S3Z? For S3, you have to do a C3, which you have already got. C3Z, then you do sigma xy. C3 you got in the previous question. What was that?
Yes, ma'am.
010 001 100. This one, and then whatever is the answer, you multiply it with xy, means z remains constant. Sorry, z changes place, xy remain constant. this one. So it will be answer D. No. Am I doing anything wrong here? So it will be 0, 0, 0, 0. First element is 0. And next element is 0, 0, minus 1. So it is minus 1. Third element will be first row, first column, second row, second column, third row, third column, like that. So first row, first column, 0, 0, 0. Answer is 0. 0, 0, 1 into 0, 0. It should be 0. 0, 0, 0. It is also coming 0. Something is wrong. Let me check. I should have solved it earlier. After C3, okay. This is wrong. After C3, when you apply, C3 is like this, C3Z. And when you apply a perpendicular plane, all the elements will invert by 1. So 1 will become minus 1. This will become minus 1. This will become minus 1. Right? So the answer should be D. Is this the answer?
Can we see?
How different? C and D are rotated. So transformed means it's like, so the C3 rotation, so this is 1, 2, 3. Okay. If you do rotation with in this angle like clockwise, you will get one matrix. But if you do anti-clockwise, you will get another matrix. Anti-clockwise is if you do rotation like this, and both will be transform of each other. Sorry, transpose of each other. Isn't this transpose? 0, 0, minus 1, then 0, 0, minus 1, then minus 1, 0, 0, then 0, minus 1, 0. So if I do transpose of D, it will become C. So they might have taken, which rotation we have taken? We have taken clockwise, no? We have taken clockwise. They have taken anti-clockwise rotation maybe. That's why the answer is C.
Okay, ma'am.
By default, you should take anti-clockwise. I think books follow if the sign is not given or it's not written whether you should take clockwise or anti-clockwise. Better to take anti-clockwise. But you should check the books, what they are doing, how the answer is being given. Okay, coming to the next question. For D2H molecule, consider the principal axis to be along z direction using the unit vectors along the three Cartesian axes as basis, the resultant symmetry operation. Okay. D2H molecule. Which molecule is D2H? A molecule which is like this will be D2H. Okay, in plane. Everything is in plane. Okay. Consider the principal axis along z direction. So the top direction is z. Okay, let us give this different name. Suppose I will write m1, m2, n1, n2. Okay, and this is x, this is y, and the top direction is z direction. Now what it is saying is using the unit vectors along the three Cartesian axes as the basis. Now here the basis is changed. In the last two questions we had the orbitals as the basis. Now here the basis is the axis itself, xyz. This is the basis. The resultant symmetry operation for sigma xy c2x is. Now this is multiplication. So let us first do c2x. c2x. If we do c2x on this, where will it be? So this is c2x. Okay. So here a will remain as it is, m1 will remain as it is, m2, here it will be n1, it will be n2. Okay. Next, if you apply sigma xy, is there any misprint in the question? It is, okay, it is only, now you apply sigma xy. Sigma xy will be this plane. Okay. C2, isn't it C2 z and then sigma xy? If we apply sigma xy, z will change.
Yeah, ma'am.
Order of, is there any role of order? Order of multiplication. It should not be. C2x. C2 is correct. Then sigma xy. Okay, sigma xy is the molecular plane, not this plane. The molecule is planar. This is what I was doing wrong. So this molecule is a planar molecule. So Z is on top. The molecule lies in xy plane. Sigma xy is molecular plane. Understood? So
Yes, ma'am.
this will be M1, M2. It will not change, and N1, N2 will change their place. This is the result after C2X. And then when you apply the molecular plane, then again nothing will happen because this is the plane of the molecule. Okay, then again it will remain as it is. M1, N2. So this result you can get by doing, can you do C2Z? Now check all the options one by one. This is the result you should get. M1, M2 will remain at their places and N1, N2 should change their places. N1, N2. This is what we want. But the original molecule is this. Now, first option is C2Z. If you apply C2Z, so Z axis is on top. Okay, it is like piercing through the plane. And then if you do C2Z, suppose anti-clockwise rotation, then it will be M2, M1, okay, N2, N1, okay. But this is not
Yes, ma'am.
same as what we want. This is different. So C2Z is not the correct answer. Do C2Y. So if you do C2Y, C2Y is this plane. In the plane Y, this is X. So if you do C2Y, this will flip like this. So it will be N2A, N1, M2, M1. But again, this and this is not same. So this is also not the answer. Now do sigma YZ. Sigma YZ. sigma yz. Where is y? Y is top and z is like this, so it will be a plane like this. Okay, suppose it's like a vertical plane on your paper or on the screen, passing through the screen. So it will be m2 m1 and n2 n1 will not change place again. So this is also not matching with this. N1 n2 should change their places. So this is also not the answer. Next is sigma x and z. So sigma x, this is x, this is y, this is z. So sigma xz is this plane. Okay. So now this is same as what we got earlier. So this is the answer. Clear? Are you able to
Yes, ma'am.
imagine the planes?
Yes, ma'am.
Okay. Uh, what about this? I think these are discussed in course.
I like C3 row.
Yes, cyclic group is C3. So cyclic group means if you do multiple operations, suppose you do one C3, then you do C3 2, you will get another element from the group itself. And then you do C3 3, 3 times C3, you get identity. So C3 group means how many symmetry elements it will have? It will have identity C3 1 and C3 2. Okay, so suppose you did C3 1 at once, okay, which is in the group. Then you do C3 2, which is C3 inverse, okay, and then you do C3 3, which is identity. It is also in the group. And C3 inverse means C3 is C3 inverse and C3 are the symmetry operations in the group. So when you do multiple operations, when you do the apply the same symmetry element multiple times, the resultant symmetry operation is already present in the group in a cyclic manner. A group of order 4 is necessary acyclic, is necessary acyclic, can be cyclic or acyclic, is always commutative. A group of order 4 can be cyclic also, acyclic also, and it has nothing to do with commutativity.
Okay, ma'am.
A order of a group is H and the order of one of its subgroup is H dash, and H dash by H is equals to P. P is a order of a group is H, subgroup is H dash. So P should be a positive integer and it should be integral multiple of that. Suppose you will have a group of order 4, then you can have a subgroup of order 2 inside it. Okay, so it should be, so 1 by, so it is given H dash by H means 2 by 4, like that. So 1 by P is a positive integer. This is 1 by P means H by H dash is P. So H dash by H is equals to 1 by P. If this is positive, 1 by P is a positive integer.
Okay.
Next one is Next one is to find the inverse. This is easy, right? This you can do.
Yes, ma'am.
What is the answer for this one?
C.
C. Okay. Uh, so how do you find inverse? What do you need first of all? This is how you find inverse, right? 1 over, suppose you inverse of A, inverse of a matrix, square matrix also is, inverse of a square matrix A will be given by 1 over determinant of A into adjoint of A. Right? So if this is the matrix, so the determinant will be this multiplication minus this off diagonal elements minus off diagonal elements. So a square minus b square, that is a square plus b square. So this should be either this or this. Now you have to find the correct adjoint, either this or this. This sign is different. So for adjoint, how you do? Adjoint is a matrix of cofactors. Now a11 will be minus 1 to the power 1 plus 1 and that element opposite to a11. So let me write a minus b, b a. This is the matrix given one. Okay. So this is a11, this is 1 2, this is 2 1, this is 2 2. So opposite to a11 is this. So into 2. This will be your first element of the adjoint matrix. This I will write capital A. A12 will be minus 1 to the power 1 plus 2. This is 1 2. So opposite to this is this element into B. Why did I write 2 here? Should be A. then A21 will be minus B. A22 will be A. So this is A, this is minus and minus plus B, this is minus B, and this is A. Okay, so your adjoint is A minus B, A minus B, B, A. Correct? This is first option.
Yes, ma'am. I think in the solutions it's given that.
Okay, okay, okay. No, no, no. This after adjoint you have to do transpose also.
Oh, yeah. Yes, ma'am.
Yes, so when you will transpose
Yes,
this, it will become A minus B, B A, and then here
ma'am.
1 over that determinant part. So this is option C is correct. Okay.
Yes, ma'am.
So you understand this one, right? How do we generate transformation matrix?
Yes, ma'am.
Okay. If you have any other doubts, you can ask, or else I will just close the session.
Nothing else, ma'am.
Okay. Are these sessions helpful, Nova?
Yes, ma'am. Definitely.
Okay.
Because like I'm seeing the lectures, but then these sessions they're making the concepts more clear for me, so it's good.
Okay, okay. And you are joining the other session also. There is one more session going on for this course on Sunday. Okay.
Yeah, I'm joining.
Okay. Okay then. I'll close this one for now.
Okay, ma'am. Thank you. Good night, ma'am.
Bye.
Bye.